Hello there, everybody. So, this is going to be just a very brief uh, introduction to physical chemistry. But this video really isn't a course. This video is merely a recreational, sort of semi-educational uh, video. So, for today's topic, I'm going to be talking about um, the very basic property of matter, which is the atom. So, if we try to define the atom, the atom, let's first try to look up the definition of an atom. The atom is basically in Greek, in ancient Greek, it means it derived from the word atomos, which means in Greek is indivisible. And if we're going to look at the physical visualization of an atom, we're going to have this structure, this sort of structure wherein there is a nucleus in an atom. The nucleus is basically just the center of the atom itself, and inside the nucleus, let's just pretend that this circle right here. I'm very sorry that I'm not good at drawing circles, but this will do. Um, So this circle right here will encompass the nucleus of the atom, which is basically just the center of the atom. And you could just imagine right here that these lines, sorry if my drawing is very, very bad and very terrible, uh, but but please don't mind that. So right here in this atom that we're seeing, very poorly drawn, um, there are lines here and the atom, and these lines basically encompass the sort of pathway of what we're now going to discuss is the electron. These lines right here are basically just manifestations of the particle of the electron. The electron is basically just a particle that is present in every atom, and it is negatively charged. And it's negatively charged. Sorry, I'm going to just use use a different color for this while I'm drawing it, so it's actually more distinctive and doesn't look crowded, because every single line so far is has been black. And we're just going to draw a line, a horizontal line inside this electron, just to represent the electrical charge of this particle. The electron is basically just a particle inside of the atom, and it's basically just a part of the structure of the atom. And this electron is always outside of the nucleus of the atom. And now we're going to be delving into the inside of the nucleus of the atom, which encompasses the protons and the neutrons. What is a proton? A proton is basically just another particle inside of the nucleus. And I'm just going to draw it as a circle in red color. Okay. So we're going to have a proton right here, and the proton, unlike the electron, um, is positively charged. The electrical charge of the protons are positive. So I'm just going to label these particles right here, just for convenience sake. This is the electron. I'm just going to abbreviate it to a letter. Electron. This is the electron. This is the proton, and this is the. I'm just going to get another color right here, and this will be the next particle that we're going to be discussing. I'm sorry about that. So So this is the next particle that we're going to be discussing that is inside the the nucleus of the atom, which is a neutron. And the neutron, I can't really add another sign right here because the electrical charge of the neutron is a neutral charge. So we're just going to leave it blank as it is. And these protons and these neutrons that are inside the nucleus of the atom, basically they depict what kind of atom you're dealing with. So the quantitative measurement of these atoms um, basically depict what kind of atom you're going to have. So for example, if we look at the atomic number, okay, the atomic number, let's zoom out a little bit, and we're just going to describe what an atomic number is. An atomic number, which you may have already heard of in your chemistry class. An atomic number is basically just the number of protons that are inside the nucleus of the atom. So we got here atomic number. So let's just assume that this atom right here is a hydrogen atom, but that will be very unlikely because hydrogen atoms only have a one single proton inside of the nucleus. So um, let's assume a hydrogen. Okay, let's quickly search up uh, the okay table elements, the table elements right here. Let's quickly just get that. Okay, I'm very sorry for very unexpected tangent. So let's dive right in. So here is the hydrogen atom, right? And let's assume that this this depiction of the atom will be a hydrogen atom. This hydrogen atom will only have one single proton inside of the nucleus, and according to I'm not sure if it's a law of physical chemistry, but according to the textbook that I've read, is that the protons and the electrons of an atom are basically equivalent to each other, meaning whatever whatever is the number of the protons that are inside the nucleus will be the same number that is outside of the nucleus of the electrons. I mean, so if we're clear on that, this will be the hydrogen atom. So let's just assume that this is the pathway of the electron. Sorry for the bad drawing again. Uh, so this is going to be the pathway of the electron. We're just going to have one single. We're just going to have one single electron outside of here. And as I mentioned, the number of protons that are inside the nucleus are directly equivalent to the number of electrons that are outside of the nucleus, and this this same rule can actually also apply to the number of neutrons, but that is strictly it is not really a strict rule because the number of neutrons are varied, which means they are approximately the same number as the protons in the nucleus, but they will not always be the same number. That like they can be just well off, farther, like for example, okay, uh, let's search up an example. Oh, sorry, I already have my textbook right here. I can just you see it's an example right here. Um, just bear with me for a moment. Like I'm just going to find an example. Okay, so here we go. It says here that the number of neutrons is approximately the same as the same number of protons as we discussed earlier. So none for ordinary hydrogen, two for ordinary helium, and about 170 for livermorium. And it says here that the atomic number of livermorium is 118. And it says that the number of protons are approximately the same number of uh, uh, I don't know. I'm sorry. I got. I have. I misspoke. The number of neutrons are basically the same number of protons, but approximately. Just approximately, because we have this example of livermorium, which is the atomic number of 118. So, which means that there are 118 protons inside the nucleus of a livermorium atom, and there are 170 or there are 170 neutrons inside of the livermorium atom. So that is just one example, but there will be multiple examples if you delve into it deeper. So let's go back to introducing the atom. Just basically a brief historical background about the atom is the ancient Greeks technically didn't discover the atom because they had no method. They had no method as we do today. Unlike today, we have the methods of knowing what an atom is. The ancient Greeks actually didn't have any methods to know or even see what an atom is, but they hypothesize that the atoms are what makes up most of our matter, what makes up our matter in general. So, but it was only until the 19th century where a person named John Dalton basically he had quantitative measurements of chemical balances, and that's when he inferred, which is basically he just drew a conclusion from a set of premises that atoms are indeed, and in fact, what makes up most of matter. So we're just going to continue here. There is also a concept of or there is also a concept of properties of atoms. So the first property of atom will be centered towards the atomic radius. So this could actually be called atomic radii with a double I. So this could also be called atomic radii, which is basically just the the radius of the atoms. That's the first property of an atom. And the second property of an atom is basically, I believe, it says right here in the textbook, we had electronic structure of the atom. This is, but we'll delve into that later. So we also have one more property of the atom. Actually, three properties of the atoms. So we have here the variation atomic radius across the periodic table. So we have here a, a an illustration of the variation atomic radius across the periodic table. So basically, what that entails is that the elements on the left, they can lose one or more electrons reasonably easily. So we have here, I'm assuming this is livermorium, but that will be basically it. But regarding the structure of the atoms themselves, I believe there's also a concept of wherein there's this person called Wolfgang Pauli, which he basically said that there will always be no 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 I'm just there can be one or two electrons outside of the atom. There can be one or two electrons outside of the atom, and if there is more than that, then those electrons, assuming that there are more than two electrons in the same atom, then those electrons will actually spin in opposite sides. So furthermore, there is also the theories surrounding the path wherein these electrons travel in. And the very first, and this is going to be just historical fact, the very first theory that was proposed by the physicist named Niels Bohr, um, he basically said that the electrons outside of the atom basically just orbit the center of the nucleus. They basically just orbit the nucleus. And this theory, this theory, which they called, oh, sorry about that, this theory, which they called the Bohr's model of the atom. I'm very sorry if my writing is a little bit um, illegible. Sorry about that. So we have the Bohr's model of the atom, which basically he just said that the electrons outside of the atom are basically just orbiting the nucleus. They're basically just orbiting the nucleus right there. Like as you can see right there, the nucleus, the electrons are basically just orbiting the nucleus. But apparently this was disproven by multiple scientists because they proposed another theory, which we can explain this and discuss right now about the Irwin. If you may have already heard what this name, or are very familiar with it. If you are a if you're if you've learned any science or whatsoever, his name is Erwin Schrödinger. You may already know him from his very famous scientific concept of the Schrödinger's cat. So we have Erwin Schrödinger. First, we have Erwin Schrödinger, and what he basically said is that these and what it basically entails is that these electrons don't actually orbit. It doesn't actually orbit the nucleus. It kind of um, the movement of electrons outside of the nucleus of the atom are more like waves, and this is where we get to the wave functions. And just to simply sum the theory up of Erwin Schrödinger uh, about the atom, about the electrons that are moving in the atom, it's basically these electrons basically just move like clouds, like waves, and we're just going to assume that this is the nucleus of the atom. So, and these electrons basically just move like waves across the atom, and the orbits they vary from SPDF orbitals, and this is just one of examples of the orbitals that are currently proved. And uh, and okay, let's get right back to the topic. Erwin Schrödinger, he just proposed that the electrons move in like a wave-like around the nucleus. So, and this basically concluded that the electrons, the nearer the proximity of the electrons across the nucleus, no, I mean around the nucleus, the nearer the proximity of the electrons around the nucleus. Um, no. Let me rephrase that. The nearer you get to the nucleus, the more likely you're going to see an electron. Okay, so by logic, then the electrons, the the farther they get outside around the nucleus, the farther they get, and then the less likely that they are to be found in the atom. Okay, sort of like clouds. If you can use analogy on this, on if you can use a simple analogy on this, it's sort of like clouds. Okay, and this is a very simple way to think about it. If you're near a cloud, a certain cloud, okay, you have one cloud like passing right by you. You can see the cloud because it's very very near. Okay, and as soon as that cloud just naturally gets farther away from you, that cloud gets very blurry, and that's basically that basically applies for a lot of things. But we could just use an analogy because it's very I could say it's very pertinent to the topic and discussion. But we're just going to get right past that abstract tangent that I just went on. So let's get back to the topic. Okay, so we're going to see right here the the first, and we already discussed this, is the first property. The atom is the atomic radii, the atomic radius, and we're going to get a little bit deeper on this atomic radius. It says here that the most important property of an atom for the compounds that it can form is its size, specifically its radius. So, although an atom has a fuzzy cloud of electrons around its nucleus, the density of the cloud falls off very rapidly at its edge. And this coincides with what I said earlier about the cloud analogy, because the farther that cloud gets, the farther that clouds. Let's just say, okay, I'm going to expand on that analogy because I think that could be a very great hook in order for us to learn this better. So let's say that I'm the nucleus, okay? Let's say I'm the nucleus, and you're, and being the nucleus, okay? Let's say I'm outside, okay? Like I'm a nucleus. Let's say I'm a hypothetical nucleus, and right above me, I can see the clouds. These clouds are supposed to be electrons. The farther they get away from me, the less likely I'm going to see those electrons. Do you get what I mean? Do you get what I mean? And this coincides with this statement that is in front of us right now. That although an atom has a fuzzy cloud of electrons around its nucleus, the density of the cloud falls off very rapidly at its edge. And at its edge, which is basically just the very farthest part, the very very farthest part, or the end of the atomic radius, which is just a very farthest part. That I'm just going to leave it at that. So speaking of the radius of atom is not too misleading. Okay. So we already skimmed through this part earlier. So, but we're just still going to discuss it. The second property of an atom is the variation in atomic radius across the periodic table. Radii typically decrease from left to right across a period and increase from top to bottom down a group. Only the main group elements are shown here. Okay, so these are called the main group elements. Okay, and I believe that there's also a topic of ionization energy. The energy needs to remove one or more electrons from the atom. As we shall see, the ability of electrons to be partially or fully removed from an atom determines the types of chemical bonds that the atom can form, and hence plays a major role in determining its properties. So the ability of electrons to be partially or fully removed from an atom determines the types of chemical bonds. Okay? So what is a chemical bond? It basically just says here in the second property of the atom is that the correlation between hypothetically the correlation between you hypothetically removing an electron from an atom basically correlates to what type of chemical bond it is, what type of chemical bond the atom will be. And we could see right here that there are um, I'm not sure if there's more bonds of for there are more chemical bonds, but we can see right here that the first chemical bond is the covalent bonds, which is formed when atoms share pairs of electrons. So let's say that we're just going to go straight back to the whiteboard right here. Let's say that we have a hydrogen atom. Okay, let's go back to the periodic table. Okay, oh, I'm sorry, I already downloaded that, but I just forgot. Okay, so we have we have a lithium. Okay, we have lithium and hydrogen. So apparently there are hold on, let me just search up the neutrons of lithium. Okay, there are lithium atoms of 3 protons, but the number of neutrons varies depending on the isotope. The standard atomic mass is roughly 6.94. Okay, so the number of neutrons that are inside the lithium atom basically varies depending on its isotopes. And we're going to let's just skip this for now. Okay, let's just skip chemical bonds for now, and let's talk about isotopes. Okay, you may have heard me already say this, but there are variations. There are variations as to the quantity of the neutrons that are inside the nucleus of every atom, and that very quantity, the difference of that quantity, the variations of that quantity will determine what kind of isotope the atom is. And that is what an isotope is. It's just a varied type of a single atom. This is a very varied type of a single atom, depending on the number of its its neutrons, from my understanding. So let's go back to chemical bonds. Okay, so let's say that we have a hydrogen bond. Okay, and this hydrogen bond is as we have already seen earlier from the illustration of the uh, table element table of elements for chemistry, is that there are the atomic number right above the left square. We can see I'm square. I'm sorry. It's actually on top of the square. Okay, it's actually on top of the square. We can see the atomic number right here is 1. So that means the atomic number of helium is 1, and that means the protons that are inside the nucleus of the hydrogen atom will be 1 as well. So if we can see here, we can draw it again. We see a positively charged proton. You can see a positively charged proton and a positively charged electron outside of the hydrogen atom. So I'm sorry, this just came out as an X right here. So we have another, let's say we have another atom, and we can just depict this atom as the lithium atom. And inside of this lithium atom, since the atomic number of the lithium is 3, we can see that the inside of the nucleus of the lithium atom will be 3 protons. We're not going to draw out the neutrons that are inside and the exact neutrons that are inside this, because we're just trying to make a we're just going to make a sort of simplified version of it in order to understand it, because there are more. Apparently, it says that there are multiple isotopes of a lithium atom, and we can't just list all of them at once. So I'm just going to assume that there are um, there are 3 neutrons in the nucleus of the lithium atom. Okay, so it says here the chemical bonds, the covalent bonds, they are formed when atoms share pairs of electrons. Okay, they can be nonpolar, which is electrons are shared equally, or polar, which means that electrons are shared unequally. So if we can just look for a picture of a covalent bond. Okay, you can just see it. Look for a picture of a covalent bond. These are very good. There's a very good illustrations because my drawings are really not good. Okay, so we have here a polar covalent bond. Okay, a covalent bond is basically just a bond between two atoms. They can be nonpolar, which is as stated earlier. They can they can be nonpolar, which is basically just the atoms sharing an equal parts of the electrons that they have, or they can be polar, which is basically just the opposite of nonpolar, which is the two electrons, the two combined, the two um, chemically bonded atoms are sharing an equal number of electrons. So if we see right here, okay, we have a polar covalent bond. Okay, hold on. So let's say this is a polar covalent bond, which is going to draw another electron outside this lithium. Okay, so we're just going to draw uh, a couple of electrons, 3 electrons to be exact. There are 3 electrons of the lithium atom. Okay, so the covalent bond basically just says that let's assume that these two atoms, the this how hold on of it's the hydrogen atom, and this is the lithium lithium atom. Okay, let's assume that these two atoms somehow were chemically bonded. Okay, due to a chemical reaction. Okay, let's say that these two were bonded. If they were nonpolar, if they were nonpolar bonds, then the electrons that they will share will be equal. Okay, will be equal. The electrons will be equal. Okay, it's an equal sign. Okay, but since the electrons, okay, let's just make a hypothesis. Okay, hold on. What chemic what bond can you form to hydrogen and lithium? Okay, this is actually an ionic. This is actually an ionic bond. Sorry about that, but we're just going to, just going to make a hypotheticals with this. I can't really stick to factual. I can't really stick to the factual depictions because I'm just trying to simply explain what all of this means. Okay, so covalent bond. We have a covalent bond. If the covalent bond is nonpolar, then as stated earlier, then the electrons will be the same. The number of electrons shared between these two atoms will be the same if they hypothetically underwent a chemical reaction. But if the covalent bond is actually polar, then the number of electrons will be shared unequally. So let's say that this is a polar covalent bond. This is a polar covalent bond. Since there are 3 electrons here, there is 1 electron in this hydrogen atom. Then we can just say, for example, we can just say for purely for exemplary purposes that this is a polar covalent bond. So move forward with the um, with the second type of chemical bond, which is ionic bonds, which is it says here that these bonds are created through the electrostatic attraction between oppositely charged ions. This happens when one atom completely transfers one or more electrons to another. Okay, so let's search for examples of the ionic bonds. Examples, okay? We can just look for the the bonds right here. We can just look for the chemical element, the element, specific element right here, which is Na, which is sodium. Okay. So if we have sodium right here, okay, we can also use this illustration right here as an example. Okay. So I'm just going to copy that, and then hopefully Microsoft Whiteboard will let me copy. Oh, it does. Okay. Okay. So let's get back to the second type of chemical bonds in chemistry. So this is going to be the ionic bond, which as you may have already read earlier from the description of the ionic bond, it basically, if we have two atoms, okay, let's say that, okay, we already have this in the illustration, so I don't need to horribly draw it again. So here's the atom one. Let's say that this is a metal, okay, let's say that this is a metal. Let's look for let's just look for the sake of a more full example, metal chemical elements. Okay. Okay. So let's say that this atom. Let's say that this atom is an iron. Let's say that this atom is an iron element. And this will be a non-metal. So let's look for examples of non-metal. Non-metal elements, which are oxygen. Let's say this is oxygen. Okay. Now I'm not going to be considering the protons and neutrons that are inside the nucleus. So we're just going to dive straight right in this example. So it's going to be a very full, semi-full example, because these really are not the same as iron. These depictions are really not the same as the depictions of the supposed depictions of iron and oxygen. Okay, so let's say that this atom one is an iron element, and this the atom two is an oxygen, the oxygen element. So what it says here in the ionic bonds is basically when let's go back right here to the let's go back right here to the description, so we can be very precise about this. The ionic bonds are created through electrostatic attraction between oppositely charged ions. So, okay, this happens when one atom completely transfers one or more electrons to another. So, what happens here? In order to make an ionic bond, we have to have one metal atom, which in this case will be iron. Let's say that this atom, the iron atom, the iron element, the neutron of the iron element, the atom, is transferred. Let's say that it's transferred inside the non-metal atom. That is when ionic molecules are born. So if you see here in this depiction right here, this is supposedly atom 2, which is oxygen. To say that for the sake of the example, this is oxygen. The atom 2 is right here. You can see it right here. This is the atom 1. And if you can see it right here, you can look closely over there. These are the supposed electrons of the atom 2. The second atom, these are supposed electrons. Okay, so if we can just count it right here, we can see that there are 7. Okay. So there are 7 electrons that are circulating around the second atom, the oxygen atom. For this exemplary purposes, I'm not saying you should take this literally, but there are 7 electrons that are circulating around the second atom, and if you see here, once it transfers an electron, the electron of the second atom will be 8. So the second atom basically just got another electron, and we can see right here. Okay, this will be our ionic molecule. This is when an ionic molecule is born through the transfer of electrons between two atoms, between two metal and non-metal atoms. So we can see right there that is an ionic bond. And I hope, hopefully, I made this a little bit clearer. So this is going to be, we're going to move right to the last form of chemical bonds, which is metallic bonds. As we can see right here to the description, it says right here that metallic bonds, very self-explanatory from the title of the bonds themselves. The metallic bonds are found in metals where valence electrons move freely among a lattice of positively charged metal ions. So if you can see right here, if you can just look for, uh, okay, you just look for metal bonds, examples of metal bonds. Okay, so we can see right here there's a metallic bond, electrostatic attraction between electrons and metal ions. Okay. Okay, I'm very sorry about that. So now we're going to be discussing metallic bonding. It says here that the metallic bonding is the electrostatic attraction between positively charged metal ions and a shared mobility of delocalized valence electrons. So what is a valence electron, for example? Let's search up what a valence electron is. A valence electrons are the electrons located in the outermost shell. So if we're going to depict an atom, okay, we're just going to depict an atom right here. Let's just say it's another hydrogen atom. Let's just say it's another hydrogen atom. Okay, we have one proton right here, one positively charged proton. So okay, we have a valence electron. So in metallic metallic bonding, as I understand it, it's basically just the mingling of metal ions. Okay, the mingling of metal ions with electrons that are out of place. Okay, the valence electrons that are out of place is basically just them like being attracted to each other. Okay, so let's just say you have two. Let's just say you have two hydrogen atoms. Okay, let's just say you have two hydrogen atoms, or three. I'm just gonna make it three. Okay, so I'm just gonna make it three hydrogen atoms. Okay. This is just for example, so I'm not using actual atoms that are included that are relevant to these chemical bonds. I'm just using this as an example to kind of illustrate what these bonds actually do. Okay, so we have three hydrogen three atoms right here. We can say that there are obviously there are going to be electrons outside. There are going to be electrons outside orbiting these hydrogen atoms. These atoms right here. There are three electrons. Going to be three electrons. Okay, so let's say that these electrons that are outside of the atom, that they're basically delocalized, like out of place from the atom. And these electrons can actually be attracted to ions that are near these bonds. So which basically just forms a, okay, let's just say that these are ions. Okay, so these electrons, the localized electrons, can actually be attracted to these ions, and they can be they basically, for a lack of a better word, they're just mingling with each other, and that creates a metallic bond. Okay, so Sorry. Let me just. Okay, okay, that's good. Okay, so I think that'll be. I think that'll sum it up for today's little preview of physical chemistry. We can actually. Well, I'll think I'll just make another episode of this and explaining where we left off in the textbook. In the textbook that I'm referencing right here, it is it's the it's physical chemistry, a very short introduction. I can't really credit the author right now because I don't know who the author of this is, but that's basically it for today's video about physical chemistry. Thank you for watching.